So these last slides of chapter 15 are going to focus on the complexing of carbohydrates into more complex molecules. So we're going to start by talking about disaccharides, which, as the prefix would suggest, is going to be the joining together of two monosaccharides to join to make a disaccharide. And then we'll shift to talking about four particular polysaccharides, which will be multiple sugar molecules linked together. So a disaccharide is going to consist of two monosaccharides, and there's going to be three different ones that we're going to spend a little bit of time talking about. The first one is referred to as maltose. It is two glucose molecules linked together. The second one is lactose, which I mentioned briefly in the introductory lecture on carbohydrates, and that is a glucose molecule linked to a galactose molecule. And the third disaccharide is sucrose, which is the table sugar that you guys are familiar with, which is the joining together of a glucose molecule and a fructose molecule. So remember that these monosaccharides listed here are the ones that I'm expecting you guys to know. And just remember that glucose and galactose are identical molecules except at carbon 4. And glucose and fructose are similar molecules, except that glucose is the aldose form of the molecule and fructose is the ketose. So we'll talk about each of these in detail. So maltose is also known as malt sugar, and it's going to be two glucose molecules joined together. And this is the molecule that is generated when our bodies begin the initial breakdown of starch molecules. So hydrolysis is basically the breaking down of a complex molecule into smaller subunits, and starch, which is the storage molecule for glucose, is broken down into these two carbon units referred to as maltose. So maltose is linked together by a characteristic bond. It's called an alpha 1 to 4 bond. We'll see that on the next slide. And all of the bonds that link monosaccharides together are referred to as glycosidic bonds. So glycosidic bond is the term that we use to refer to the joining together of monosaccharides to form more complex molecules. This is going to be a molecule that's used in things like cereals, candies, or brewing. And it's going to be found in two different forms, the alpha and the beta form, which we'll talk about in just a minute. So anytime that we are joining together glucose molecules, just as we saw in joining together alcohol molecules in the organic chapter, when we do that by the removal of a water molecule. So maltose is joined together by an alpha 1 to 4 linkage between two glucose molecules. The alpha refers to the position of the OH at carbon 1. Remember that carbon 1 is the carbon that forms the ring. It's called the anomeric carbon, which means that the OH can either be in the down position or the up position when the molecule goes from the open chain to the closed chain molecule. Now when the orientation is down, that's the alpha version of glucose. So alpha D-glucose is joined together with a second alpha. This is an alpha D-glucose molecule here. It's joined together by the removal of a water molecule and the formation of an oxygen bridge between carbon 1 of our first glucose molecule and carbon 4 of our second glucose molecule. Remember that we draw these in a way that carbon 1 is always positioned at this point in our molecule. So this is carbon 1, this is carbon 2, 3, 4, 5, and 6. Over here, carbon 1, 2, 3, 4. So the O linkage occurs between carbon 1 of our first glucose molecule and carbon 2 of our second glucose molecule. Now this is referred to as alpha maltose because the second glucose molecule, which has an anomeric carbon that can open and close the chain. This is oriented in the down position, so it's the alpha anomer. If the OH was up here, it would be referred to as the beta anomer. So that is maltose. Lactose is the disaccharide that we find in milk. And again, it's going to be the formation of a galactose, and specifically the beta form of galactose, with either an alpha or a beta version of glucose. There's going to be a beta 1-4 glycosidic bond, and again, that's because of the beta galactose that's utilized. And again, it's going to be found in milk and milk products. And again, because the glucose molecule can convert from the open to closed chain, it can go back and forth between the alpha and beta forms. So this is our galactose molecule. In the ring form, remember that galactose and glucose are different only at carbon 4. If you look at carbon 4 in galactose, the OH is pointing up, whereas the OH in a glucose molecule is pointing down. Our galactose is the beta D-galactose molecule, so the OH is pointing up at carbon 1. In this case, the glucose molecule is an alpha version, and the OH at carbon 1 is pointed down. The linking of these two molecules is between the beta OH of galactose and the OH of our glucose molecule. So it's depicted as the O going up and the O of the glucose molecule going down. So it's kind of like a little bit, the glucose molecule is written a little bit above that to be able to get this kind of orientation here. This is referred to as the beta 1-4 glycosidic bond. Beta because the OH on the galactose was facing up. And the 1-4, the 1 because galactose, at the OH of carbon 1 of galactose and the OH of carbon 4 of glucose are joined together. Now the joining together of our two monosaccharides, again, is the result of the removal of a water molecule, which is shown here. The third disaccharide we're going to talk about is the molecule sucrose, which is also known to you all as table sugar. It's obtained from either sugar cane or sugar beets, and it's the joining together of an alpha D glucose with a beta D fructose molecule. So again, the alpha is the OH pointing down, and in this case, the fructose is the beta version. Remember that fructose is a ketose. So when the chain closes, it's closing at carbon 2. So at carbon 2, the OH is pointing up, which makes it the beta anomer. So just to draw these two, the easiest way to do that is to draw the glucose molecule on top and the fructose molecule on the bottom. So again, we do this by the removing of water, which you see here, and this is referred to as the alpha-beta 1-2 glycosidic bond, because both of these molecules are locked in to their conformation because of the formation of the glycosidic bond. So the alpha is referring to the glucose molecule alpha, which is at carbon 1, and for the fructose molecule, the beta is designated for carbon 2. So the beta was the OH pointing up. So the alpha comma beta 1-2 glycosidic bond that forms sucrose. So the discussion that we just did here would hopefully help you guys work on homework problems number 1534, 1544, and 1558. So you can pause the lecture and go and work on those homework problems now, and hopefully you'd be able to make some progress on those. So sweeteners, primarily the mono and disaccharides we've been talking about, are ranked, or they're given a value for the relative sweetness as related to sucrose. So sucrose is our reference standard. Again, that's table sugar. It's given a value of 100. And all the other molecules are given a value in relation to that. So you can see that several molecules like maltose and lactose have a very small amount of sweetness compared to sucrose, where a molecule like fructose actually has a greater level of sweetness compared to sucrose. So the fructose that you would, if you were to taste a pure form of fructose, then that's going to be quite a bit sweeter than the table sugar that you all are familiar with. You'll also want to remember that the sugar alcohols that are formed from the reduction of a sugar are also relatively sweet. Sorbitol is the sugar alcohol that results from the reduction of glucose, and you can see that that has a sweetness of 60, while other sugar alcohols have an even higher relative sweetness. Artificial sweeteners, you can see that our non-carbohydrates have a tremendously higher level of sweetness compared to sucrose. Again, these are ones you'd be familiar with. So aspartame and saccharin are going to be the most common. So all sweeteners are given a value of relative sweetness compared to sucrose. That brings us to polysaccharides. Polysaccharides are the joining together of multiple monosaccharides, so poly being many. Now the polysaccharides that we're going to talk about are all going to be polysaccharides of glucose molecules. So it's a different way of joining glucose molecules together to form other molecules. Now several of these are going to be simply a means of storing glucose for later use, while one of the molecules we'll talk about will be a structural molecule in plants. So the molecules that we're going to talk about two different kinds of starches. So amylose and amylopectin are both starches that are made of alpha-D glucose. Glycogen is going to be very similar to starch, and it is the storage molecule for glucose in animals. This is the molecule that is stored primarily in our liver, but also in our muscles, that our bodies go to for a ready source of glucose when the need arises. Now cellulose is going to be the structural molecule that we have in plants, and that is made of beta-D-glucose. So the storage molecules for energy are all the alpha version of glucose, and the structural molecule cellulose is going to be the beta version of glucose. And again, the only difference is the orientation of the OH in the closed chain or the ring form of the molecule. So we're going to start out by thinking about the starches. There are two different versions of starch. Amylose is an unbranched version or an unbranched chain of glucose molecules, whereas amylopectin is going to be highly branched. So we'll start by thinking about amylose. Amylose, again, it's a polymer of alpha-D glucose, and it's going to be linked by a 1 to 4 glycosidic bond. So again, this is carbon 1. Well, actually, this one, I'll go ahead and talk about this one. This is carbon 1 of our first glucose molecule that's participating in the bond. And this is carbon 4. So the alpha is because the OH was pointing down when our ring closed. And again, because the glycosidic bond is formed, that locks this carbon into that orientation so it can't change. The ring can no longer open and close because of the formation of the glycosidic bond. So this is an alpha 1 to 4 glycosidic bond. And again, the amylose chains are unbranched chains of glucose molecules. Amylopectin is going to be very much similar to amylose, except with the addition of an alpha 1 to 6 branch point. So the long chains are going to be the same as amylose in that they've got alpha 1 to 4 glycosidic bonds between adjacent glucose molecules. However, there's an alpha 1 to 6 branch point that occurs every so often in the molecule. So that means that at the branch point, we have one of our glucose molecules with the alpha OH at carbon 1 connected to the carbon 6 of a glucose molecule at the branch point. So this is referred to as the alpha 1 to 6 because the OH was pointed down at carbon 1, and it's connected to carbon 6 of our branch point glucose molecule. So the alpha 1 to 6 glycosidic bond is the branch point. So both amylose and amylopectin are the storage starch molecules of plants. Glycogen is a polysaccharide that stores glucose in mammals, both in the liver and in muscle. And again, it's the alpha version of our glucose molecule. It's going to be very similar to amylopectin in structure. The only major difference is that it's much more highly branched. So again, it's going to have alpha 1 to 4 linkage glycosidic bonds for the main chains, or alpha 1 to 6 glycosidic bonds at the branch point. Cellulose is the polysaccharide of glucose that is a very important structural molecule in plants. Now the major difference is that this is going to be the beta version of glucose. So the joining of the molecules is beta 1 to 4, is the beta 1 to 4 glycosidic bond. So what this means is that the glucose molecules that are used to make cellulose, at carbon 1, the OH is pointed up. So the joining together of our glucose molecules is still connecting carbon 1 and carbon 4, but the major difference is that the OH of our glucose molecules is pointing up and forming the beta anomer of our glucose molecule. Now this is absolutely critical in the formation of cellulose, and it has a major impact on the ability of organisms to utilize glucose in this form. For example, even though the connection is still 1 to 4, because it goes from an alpha connection to, from the alpha anomer to the beta anomer of glucose molecules, so humans are completely incapable of getting any dietary benefit from cellulose molecules because we don't have enzymes that recognize this glycosidic bond. This will mean more to us as we discuss the metabolism of carbohydrates in chapter 22. So as we think about the joining together of glucose molecules to form polysaccharides, it's important to understand the different types of glycosidic bonds that form cellulose compared to the starches or energy storage molecules of starch, of amylose, amylopectin, and glycogen. So cellulose is a beta 1 to 4 glycosidic linkage, and amylose and amylopectin are alpha anomers of carbon. Amylose is the unbranched version with alpha 1 to 4 glycosidic bonds, whereas amylopectin has the alpha 1 to 4 glycosidic bonds for the long chains, and then the addition of alpha 1 to 6 glycosidic bonds for the branching that occurs in amylopectin. So this discussion should help you with homework problems 1540 on page 556 and 1554 on page 570. So go ahead and give those a shot and see how you do.